Hey guys, this is Lego Master 99 here again today, or Duncan, and today this is going to be a video, or maybe a few videos, I don't know, depending on what happens in this video. This is going to be a video, or more rather a tutorial on how to program and actually operate this behemoth of a redstone mess here, what I like to call a computer. But this is, yeah, most of you guys should recognize this from a few videos ago. All those posted almost 6 months ago, from the date of this recording. So, yeah, I've been really busy recently, or for a while mostly. So, yeah, just some people expressed that they wanted to program this, and some people actually have, based on the information that I gave in the the quote unquote manual, or the doc that's in the world download that's in that video's description. But some people were confused, and I was going to make this video anyway, and I've been postponing it because I've been really busy with other things. So I'm going to finally make this video and show you guys how to actually program this computer to do mostly whatever you want. So yeah. All right. So for the first step of learning how to program this computer and having the ability to be able to program your own programs is um, there's some steps that you need to go through, or you don't need to, but it'd be nice to go through to help you to learn. Um, and you need to learn how this computer works, or you don't need to learn how it works, but you just need to learn the instruction set. And that's what I'm going to go over now. And let's just go over here, and I'm going to talk about the Debugger Center in this video, or videos coming up soon. So, alright, so here's the Debugger Center, just quick view of it. I'm going to go over this later, as I said before. So, the first step in learning how to program the computer is learning how the instruction set works. And as I detailed in my, or went over in my release video of this computer, there are 4 different program memories, and it's one for each core. And the distinction here is that each of these are pretty much separate. The only thing that's connecting these all these together is one bus and the RAM. So these are pretty much separate. So if you want to program a program, like let's say just a simple Fibonacci program, like I demonstrated in my demonstration release video, you don't want to be writing multiple lines of code over multiple cores here. So if you have one program, you write it on one section of program memory at a time, and you can tell what the sections are by this whole block here. So you see this black block 1, and then down here is 2, and then 3, and then 4. So you don't want to be writing like 3 lines of code for your program on this one, on core 1, the core 1 program memory, and then doing the next 5 lines on core 2, and then the next 3 on core 3. The program won't work. I'm telling you that now. So, but anyway, enough rambling. The first part up here, I guess we'll go over the top of the program memory. So these first 5 bits here, this is the conditional test part of the what's it called? The instruction set. I'm forgetting everything because I haven't really touched this computer in a while. But all right, so these first 5 bits here are the condition test. And as you can see here, they are labeled 1, 2, 4, 8, and then 16. So least significant bit is on this side, and most significant bit is on this side. And with all of these, there will be signs on the respective bits showing their respective values. As you can see down here, 128, 64, 8, and then we have 1, 8, 8. And so that'll be true for all of them, and I think it'll be true for all cores as well. Yeah. So every single core should have that. They should be identical. Oops, I bumped my mic. Sorry, guys. RIP headphone users. But they should be identical. But if they're not, just reference the bits here, and you'll be able to use that, and then the doc and this video to be able to program the right things in. So I'm just going to use core 1 as an example here, and there's 5 bits. And if we go over here, which decoder is it? It is this decoder here. So this condition, basically you're able to input a condition based on the value that you input here, and it's encoded so that you're able to there's the ability to have uh, more conditions to be tested. So the conditions to be tested are shift overflow, shift underflow, E equals B, A is greater than B, less than B, and then the 4 computer inputs. And I think there's an RGB somewhere here, and there should be, and it's alright. So as you see, they are very conveniently labeled here, and it was actually for mainly my own benefit since this got so messy I had to start labeling things. But this is basically an order, so this is 1 in binary, this would be 2 in binary, 3 in binary, 4, 5, 6, 7, all the way down. And then if you know, you should know how to count in binary, and if not, I might release a series on binary and computer science and all that stuff in general. But just use these signs here as indication of values to determine this. So if we wanted to test for computer input 1, let's see, which is 1, 2, 3, 4, 5, 6. So this is condition 6 to test. And then I would put down, this is just an example, I would put down like 2 and 4, so that's 6 for binary. So then you put that down on whatever line of code you needed it. And then that would tell the computer that you wanted to test for computer input 1. Alright, so the next 5 bits here are, I think, let me reference my notes here. Alright, it is the, and I think this is purple, right? Yes, okay. So this is the true ID. So basically, the way the go-to system works for this is that you have, or the conditional branching. So if you have a test, so you have a test here, and then you have a line of code if that test is true, and then a line of code if that test is false. So for most purposes, you would need to have all 3 of these at least have something in them so that your program is able to work properly. Mostly, I don't really know your intentions to program with this, so we'll see what people come up with, you guys. So this here are the 5 bits that you put in for the false. So let's say we went with our computer input 1 example, and let's say if the computer input 1 was on, go to line 5. If not, go to line 6. So, and then this false would be where you put line 6. And then, as again, they're denoted here, the different values. So just determine the line of code you want to jump to, and then we'll talk about all that later. And then just write it out here on whatever program line you need. And then this is basically the same thing except for true. So if you like hit a condition and it's true, then it'll read off of this bus here, and or off of these bits, and then it has the same value, so you can basically use that to determine the value. Alright, so that is the go-to part of the instruction set in this computer. Alright, so the next part and the biggest part of the instruction set is all of this down here, which is pretty much the actual instruction itself, minus the branching and stuff, which is up here. So all the rest of the instruction, oops, I fell down a little bit. So all the branching stuff is up here, and then all the actual instruction data stuff is down here. So let's see here. Alright. So I'm going to go over what each of these colors signifies. So I guess we'll start with the red, how typical. So the red here, these 5 bits, is the opcode. Yeah, so these denote the operation code, or opcode for short, of what you want to perform. So if you wanted to add, you would put, I think it's 1, and then you could probably just follow the wires and then look at the decoders here, since most of them are labeled. Yeah, ALU add is 1, and then ALU subtract is 2, and then all the way down. So, and that's also in the manual. Most of this is in the manual already, but for you visual people, you can physically see it. So this is where you denote all of your, or this is where you put all of your opcodes for each line of code that you want to perform. This here, I think, is the RAM. Okay, so this is the RAM read bus here. No, I keep getting this mixed up. I'm sorry, guys. These are the 4 bits to signify what RAM address you want to read from in your instruction. So if you wanted to, let's say, add, let's say you wanted to, no, let's say you wanted to copy something, right? So you wanted to copy something from RAM 3 to RAM 4, then you would read RAM 3 here, and then write RAM 4 here, and that leads perfectly into the RAM write. So the cyan here is the RAM write. So if you had an opcode selected, if you in your instruction you want to do something regarding writing to memory, you would put the certain address of memory that you want to write to here. And then here, these last 8 bits are basically what I call instruction data. Yeah, pretty much instruction data. And this, they're split up into, it's pretty much 8 bits, but it's split up into two 16, or yeah, it's split up into two 4-bit values here. And I think those can be used in the computer, but this is basically if you want to pass information directly to whatever ALU you're working with, since I think each one of these has a direct connection. If we follow the wires, and I know this is a fact, but I'm just showing you guys. If you follow the wires down here, it makes a direct connection to our ALU input. So that is where that goes. So if you wanted to say, like, let's say, add 1 to RAM at 1, then you would, read RAM 1 and then put 1 in here and then select add. So that's where all the quote-unquote immediate or quote-unquote instruction data goes. And then going on the right side of our opcode bus here, this is the dual read bus, I think. Yes. Okay, so this is in the doc, it's referenced as the RAM control ID. And if we go down here, they should be labeled. That's right. Okay. So these 2 bits basically enable or disable dual read mode, because in this computer, the RAM, as I think I said in my demonstration video, this is dual read RAM. So we were able to write 1 byte of memory at a time, but we were able to read as under 2 bytes of memory, 2 completely separate bytes of memory at a time. And, excuse me, in order to enable that, you would toggle, I think, one of these bits, and they should be labeled. If you're curious about whatever like values mean, just follow the wire. There should be a sign or something somewhere down the line showing it. So this bit here, I think this is bit 0. Oh, it's bit 2. Never mind. This bit denotes whether you want to enable or disable dual read mode. And then if this bit is on, the write becomes your second read. So if you wanted to, let's say, add two variables together, or 2 values in memory, 2 locations in memory, you would do add and then toggle this dual read bit, and then your 2 locations in memory that you want to add together, and then that will read 2 bytes of memory at a time. And now this bit here basically determines whether you want to read RAM A or RAM B, and that's in single single read mode, so not dual read mode. So if this bit over here is disabled, you have the flexibility to be able to control which read you want your value going through. Since by default, whenever you read from the read bus, it will read off of RAM A. But if you want to read off of RAM B, and there are a couple of good reasons for that, I think, you can just toggle that bit, and then you'll be able to read off of RAM B instead of RAM A in single read mode. And I think that covers the RAM control bits. And then the last 3 bits here are dedicated to what I call special flags. There you go. Special flags are operations IDs. And this is basically like more detail, more information for an instruction. So let's say you wanted to test for that's in there already. Let's say you wanted to output some data to our 3-digit display up there. The way you would do that is that you would, for the opcode, you would put IO output, which is self-explanatory, output data, and then to signify that you wanted to output to specifically the decimal display, you would put a special operations ID in here, and then it would go ahead and select that specific place to output your data or whatever data you have. And I'll go over all this more, but that was just a brief overview, as brief as I probably hopefully could have gotten it, of the instruction set of this computer, as I called it in my video, the quote-unquote a guy who is bored primary. But yeah, that is pretty much an overview of the program memory. Okay, guys, so now we're gonna continue our journey here to learning how to program this computer. And now we're going to actually begin to program, or not yet, but almost. We're close. So now we're going to have to determine which core we want to write to. And you honestly can choose any core you want, but for me, I'm going to choose core 1 because usually core 1 is like the fastest one by like just a little bit, since it's closer to the core, like the center here. But in this particular computer, it doesn't really matter which one you do, which core you select. Well, I mean, it doesn't matter in general, but especially not in this case because all the wires are very close to each other and its latency isn't as long as it could be. And then now, once you've selected your core, so for me, I've selected core 1 that I want to write my program to, you want to make sure that the entire program memory is clear of any data. So as you can see here in core 1, there's still some data here, and I think this is either the Fibonacci program in the demo or the multiplication program, one of those two. And as you can see, there is still some torches in here which indicate data. So I'm going to go ahead and clear all of this, since if some remnants remain, it might cause instruction corruption, which like there's torches that you forgot to remove and then it does unintended things. So I'm going to go ahead and remove those and then I'll meet you guys back. Alright guys, so I have gone ahead and cleared the program memory here for core 1 of any data. So as you can see, it is now completely empty. And after you've done that and then you've made sure that there's no extraneous data on here that could interfere with your program, now this is kind of just a thing for me that I like to do. And it's evident in the doc that I put in the world download and also my future computer projects and everything. But I like to write out my program before I go ahead and program it, so that I know what I'm doing and so that I know which direction I'm going in, so that I don't have to change everything, since this is like just ones and zeros and it can get very confusing very quickly. So I'm just going to go ahead and do a program that's in the doc here, and I'm probably going to do a couple more programs, and those may or may not be in this video, but you'll guys have to look around. If they're not in this video, I'll link them in the description or somewhere for it, so that people that are just that know how to program this computer already, that only need like a little like advice on some things, can get it, and then they don't have to sit through like an entire maybe hour-long video. I don't even know how long this is going to be. But anyway, I'm rambling on. So let's get started. I'm going to go ahead and program a very simple program here that's in the doc. If you scroll down to like the more bottom, near the bottom of the page, it says computer test programs, and in the first program it says counting program. I will go ahead and program that for you guys here. So in the doc, it's already all written out, and I have lines of code and everything, so let's begin. Alright, so for line 1 of code for this counting program, the doc says write 1 to RAM address 1. So this is line 1 of code. And when the computer starts, when you hit the on button and the specific core is selected, the computer will automatically initialize the program for you. And that's basically a bunch of fancy talk saying that the computer will load line 1 of code for you, so that you don't have to like do any fancy stuff here. Let's see, like right here, see, this will turn on when the computer turns on, and then it'll load line 1 into the the branch control unit buffer here, the register, sorry. So, alright, so enough of that. So line 1 of code. So basically each one of these black lines here is one line. So this is line 1, line 2, line 3, line 4, 5, 6, 7, 8, all the way down until I think 20 right just over here. Alright, so write 1 to RAM address 1. So let's see, we want to write to RAM address 1, so I think it is this cyan here, if I remember right, and we can go ahead and look. Actually, I'm going to go ahead and reference the doc in this video, and the dock itself is actually very useful for programming. That's why part of the reason why it exists for you guys. So it's not gonna harm you guys if you look at the dock a lot. It's okay. I'll do it too. All right. So it is RAM right, and let's go ahead and go back to our program here. So this is RAM right, and you want to write 1 to RAM address 1. So this, putting a torch here, since this is 1 in binary, we're going to write to address 1, and now I just need a value, and we're going to put 1 here, since as you see it says 1, and then this is the immediate value. So this should go straight to the RAM, and then it will go ahead and write that for us. All right. So after that, we will go ahead and program. Okay, so the way we'll do it is that we'll do all of these, the actual instruction, and then we'll program all the go-to at the, next. All right, so line 2, we're going to skip over here. We need to write 1 to RAM address 2. So now we're going to go ahead and write to RAM address 1 again, and then the sign's up here, so it says 1. And let's see. I think this is also 1, so we're going to go ahead and write. Oops. Yeah, you have to be careful here. You fall a lot. But all right, so we're writing 1 to RAM address 1, and this is not RAM address 2. This is RAM address 2 right here. All right, so now I'm writing 1 to RAM address 2. Now the next line of code that's in the doc, add RAM address 1 to RAM address 2, and then in parentheses enable dual read mode. So we're going to go ahead and do the dual read mode first, and that's easy. We'll just turn that toggle bit on. And now the opcode, or the code here to add, I think is 1. So we'll go ahead and turn 1 on. And then if you're unsure, you can just look at the decoders. And they usually, these red decoders usually have it. So yeah, ALU add is line 1. So let's see. So 1, and then since we have dual read mode, we're going to go ahead and specify both the 2 addresses we want to read. So we're going to read from RAM 1 and from RAM 2. And there's a little note in here that says RAM read is cache A and RAM write is cache B. So basically that means RAM read is going to be the first number to add, and then RAM write, this here will be the second number, so then it'll be RAM address 1 plus RAM address 2, which is basically what this line of code here is saying. And then for the next line of code, let's see here. All right, so that is okay. All right, so we'll go to line 4 here. Where's line 4? Here it is. And then we will worry about the go-to stuff later. So line 4, write output to RAM 2 and output decimal display. So we're going to go ahead and do the write part first, since we know that. We're going to go ahead and write to RAM 2 here. So this is address 2. And then the way this works is that you don't need to specify like output add or anything, because after your ALU operations, which is like add, subtract, compare, bit shifting and stuff, the output will be available. I'll just say available for now. I'll show you later when we get to debugging. But it'll be available, and then you're able to, in the next line or any lines after that, you're able to manipulate that output using this line of code here until you don't want it anymore. So we want to write to RAM address 2 this output that's available, and we want to output it to the decimal display. So I think IO output is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, see here, IO output is 9. So you can also reference the doc for this too. I think it's also in the doc. So 1 and 8. And now the operations ID here, since for IO output, to be able to perform this, you need 3 things. You need, first of all, some data, which we have because of this add command that we performed previously. We need the instruction ID itself, so the opcode, and then we need the 3-bit operations ID here to specify which display to output to. So if we go ahead and look in our notes here, this is going to be just a lot of me looking in the doc, so you guys should probably follow along, and then you'll see what I'm doing. Okay, let's see. Okay, so in the middle of the doc-ish where it says IO output, we want 3-digit decimal display, which is that up there, which you guys should know, and that is 0, 0, 1. So I think that is 4. So if we go ahead and go like that, oh, that's 1. Never mind, excuse me. So let me check here real quick. This should be IO output decimal display. Okay. All right, so let me just follow the wires. And usually sometimes it's following the wires and stuff. But let's see, where does it go? You know what? Okay, screw it. We will leave this for now, and then in debugging, if it's right or wrong, we'll go ahead and correct it. That's entirely why the debugger center exists. Since if you try to follow the wires like I just did, it'll get very messy very quickly because it's pretty much just a mess of wires. So after that, that line of code is to output to the decimal display, and then the next line of code here, line 5, is to flush the output register. And what that means is that since we are done using the output from this add command, since it's saved in a register, which means we can manipulate it until we don't want to, this flush output register basically means we are removing the output from the quote-unquote available area, the available space. So if we flush the output register, in the further commands we cannot use the value from our add command. So I think flush is, let's see here. Flush is 1, 2, 3, 4, 5, 6, 7. So it is opcode 7, and then we will go 1, 2, 4. So this is 7 in binary. And then we need to specify our ID to flush, and then if we go ahead and look in our doc here, reg flush. Okay, so it says 1 for core output register. Alright, so this basically means we will be able to reset the value that the add command gave us. And now, that's basically it. And then we have a line, it says in the doc line 18 to shut down the computer, so it can be anywhere else, but just for convention, or not for convention, but for like, what is it? For, like, since it's in the doc, it says that in the doc, we will go ahead and put it there. So this is line 18, this is 19 and 20, and then we will shut down the computer. And for that, it is ID 9. I think I know that for sure. Oh, wait. No, it's not ID 9, is it? It is not ID 9. I think it is ID 12, actually. 1, 2, 3, 4, 5, 6, 7, 8, 11. So it is 11. All right. So you'll go 1, 8. Okay, so this is 9, 10, 11. All right. So now when you go ahead and execute a shutdown command, you will not need anything after that, because once the shutdown command is read, it'll go ahead and reset everything in the computer. And if you specified it in the control panel up here, there is an option here, clear RAM and UI outputs on shutdown. And if you flip that, it'll also reset the RAM and the data that's in here and in here, since it'll store it for you. All right. So that is pretty much all the instruction stuff, and now we will get to working on the go-to stuff. Alright, so for the go-to, this is pretty easy until we get to the branching part, which is the quote-unquote if statements, or they are the if statements, but in this case in this computer and for future computers, I'm going to call it branching, since we are, well, I'll explain it when we get there. So for line 1 of code, since that is the starting line, when line 1 is read, it'll go ahead and read the next line of code we want to go to. So I think alright, so these 5 bits here, the magenta, is for the false condition, and this is the true condition. So if you have a condition specified, and I explained this earlier in the video, you have a condition, and then this is the line of code it'll go to when it's true, and then if it's false. And since it's false by default, since we have no condition to test for, it'll always be false. So we want to put our next line of code here. So we want to go to line 2, which is RAM writing 1 to RAM address 2. So we're going to put a torch here to specify that we want to go to line 2. Now in line 2 here, we want to go to line 3. So we'll put 3 in binary here. Oops, there goes my phone. Sorry about that. I'll go ahead and silence that. But for line 3 in the doc, it says if shift overflow equals false, then jump to 4. If it's true, then jump to 18. So I will go ahead and program that in, and then I'll explain that to you guys. So basically, shift overflow is a condition that's in this computer when the output of anything exceeds the 8 available bits here. So if you get, like, let's say 255 plus 3, then that'll give 258, and that this computer cannot physically hold 258 in its architecture. So then that'll give us a shift overflow error, and so the number is too big to hold. So since we want to test for shift overflow, and then in the Docker test 3F and 3T for that, we want to go ahead and test for shift overflow, and that condition ID is 1. So we're going to put 1 here for the condition ID, since we want to test for that, as you can see, shift overflow. And now we want to go ahead and put down our 2 lines of code if it's true or false. So if we do hit a shift overflow, we want to go to line 18 of code, which for the true you would put it here. So then that is 16 and then 18. So 16 and 2, which would be 18. And then for the false, we want to go to line 4, which is right here. And so the computer go ahead and determine that, and then if it's true, it'll jump to line 18 of code, which we programmed this a little bit earlier. As you can see here, line 18 is computer shut down. So since anything after 255, which is the limit of this computer, if we get anything after that, the results are inaccurate since it can't physically hold the answer. And then for false, we'll just jump to line 4, which is outputting to our decimal display. And then writing to RAM2 as well. And so now we're on line 4. We want to go ahead and go to RAM5. So let's see, 1 and 4. And then on line 5, we want to jump back to line 3, which is adding and then going through this entire thing in. So once we jump to line 3, that we created a loop here. So now the way this program will run is that it'll run the first 2 lines of code, and then it'll run all the way to line 5, which is here, and then on line 5 it'll jump back to line 3 of code, and then it'll basically loop these 3 lines of code over and over and over again until this condition here, this shift overflow condition, is hit true. So if the shift overflow occurs, which means we've finished our counting pretty much, then it'll go ahead and shut down the computer. So that is pretty much it. That is the go-to system. Now, the thing is, though, is that the longer your program gets, the slower your clock speed will have to be, because with this here, okay, it's not with this, but in general, as you have more lines of code, it'll take just a fraction of a bit longer to access it. So in like future computers, if I have like ridiculously big program memories, maybe, I don't know, wink wink, it might take a little longer to access. So that's why we have our program in like 6 lines of code. So that is enough about that. This is the counting program programmed in our computer. Alright, so sometimes it actually is really that easy, and sometimes it can get a little more complicating. In this case, it was pretty easy since this is a pretty simple program. And that's why, once it gets more complicated, that's why I want to write down what the program will do. So now, we are going to go ahead and test our program. So the way this works is, alright, so pretty much we do not need to touch, for testing, we do not need to touch any of this up here. The only thing we do need to worry about, though, is the program settings here, and only a fraction of it. So it's for here, these 2 switches are relevant to our programs, or to most programs. So if we want to clear the UI outputs on shutdown, we're going to flip that switch. I'm going to leave that blank so I can show you guys what's going on here. But it won't shut down, so I'll just leave it like that anyway. I like it like that. And then for this, report program exceptions to I/O, I will leave this on so that when we do hit a shift overflow, you will be able to see it in this program output panel. So if we have that off, the shift overflow that we're testing for, if the condition does become true, then we won't see it here. So we're going to leave this on. The clock speed is relevant since we're going to be using the debugger center, which is, pretty fun. And now the last thing here for this is extremely important. And it might be left like this, might have core 1 on, but hold on, I'm going to go in and turn my settings on. I'm noticing a bit of lag here. Alright, there we go. It's kind of laggy up here anyway, but you want to have the core enabled, or cores if you're writing a multi-core program, which is advanced. But since we programmed our program in line 1 of code, which is right here, not line 1 of code, in for the first core, which is right here, we want to go ahead and flip the switch for core 1, since if this switch isn't on, then the computer will not even bother running anything on that, just to make it less laggy. So, alright, and then as you can see, once that indicator turns on down there, then the computer has recognized that we want to run our program at core 1. So now to the actual debugger center part. Alright, so now we're going to go ahead and I'm going to go ahead and introduce you to the debugger center. Well, you guys have seen it in the never mind, in the last video, maybe, I don't think so. I think I probably cut that part out, but one small change, I turned this back on so that when we shut down our computer, it'll wipe everything. But when the program is running, they won't reset, so you'll see what I'm talking about. But to get to the debugger center, which is self-explanatory, it's a center for debuggers. It is right here, teleport to debugger center. And that teleports you down here. And now this is actually a really, I think, a pretty cool place. This is where I put all of the computer's reigns right here, and all these buttons and stuff. And hopefully it won't be too confusing, but it hopefully won't be too hard for you guys once I show you how to use it. And this is actually going to be extremely useful for debugging your code that you've just written on your computer, on this computer. So the first thing you want to do when you just come down here is that you want to go ahead and see load first line of code in the computer manual power on. Now you're going to want when you want to start the program and turn the computer on, first of all, as I said before, make sure your core is on that you want to use. Now if you click this button, you can see you heard the piston go off. Now and then usually it's best to wait for, as you can see, if anything happens in here, you want to wait for like a low number of chunk updates, because if there's a high number of chunk updates, that probably means that the computer is still doing something and Redstone is still moving around, and you don't want to run too many things at once here, else the computer might break or something. They might have to shut down and start all over again. So just a quick tip there. But anyway, we have loaded our first line of code into the computer. And if we look over here on core 1, since we enabled core 1, as you can see now, this is off, which means that it is being read currently. And as you can see, since we manually turned the computer on, now we are reading the data here. So we are reading write to RAM 1, and then we're reading go to line 2. And now, since we saw that this worked, and actually, just a quick note here, when you turn the computer on, the instruction will always be one behind the actual one. So what I mean is that since it says line 1 of code here, and since we're actually reading line 1 of code, and what does the output up here say? Since it's also outputs, yeah, see, it says line 1 for core 1 up here, and that's pretty nice for people to see if they're up here and they can see the thing that looks pretty cool. So we're actually on line 0 of code. But although we are reading from line 1, we are actually executing line 0 of code because there is nothing in these registers yet. It's completely blank. We are just reading. When the computer clocks, though, it will go ahead and update these registers with the data that's here. So basically line 1, and then it'll load line 2, and then so on and so forth. So to clock the computer or load the next instruction, we press this button here. It says increment line of code. And if we press that, as you can see, our chunk updates are going up pretty high, and then I'll wait for them to go down a little bit. Alright, so now we're at 0 again. And that basically incremented our line of code. And since we told the computer to go to line 2 of code from this torch right here, as you can see, it's jumped to line 2 of code. But actually, we are executing line 1 of code because the first line of code is now loaded into these registers here. And since we are debugging, let's check to make sure that we are writing to RAM address 1. And this is the tedious process of debugging programs. And that's why the debugger center is so useful, so that you can run one instruction at a time and see if everything's working properly. And as you can see, we have a 1 coming in here, and then this line indicates that we are writing, and we are indeed writing 1 to RAM address 1, which is good, which means that line 1 of code is doing what we want it to do. And then if you want to see line 2 of code, we're going to go ahead and go here again, press increment line of code, and then I'll let the computer update. Alright, I'm just looking at the chunk updates and then waiting for it to go down. Alright, so now as you can see, we're on line 3 of code, but we were actually executing line 2 of code, if that's confusing at all. So we were basically reading the next line of code, but actually executing the line of code before that. So we are executing line 2 of code, which should be, again, writing 1 to RAM address 2 this time. And as you can see, 2, and then we have 1. So that is good. It is doing what we want it to do. And now for line 3 of code, if we want to see that executed, we're going to press increment again. And now this instruction might take a little bit longer to process. And I'm going to go and start walking on all those. You see the chunk updates are pretty high right now, and it's staying there for a little longer. But let's see if our add command is working properly. Let's see. Since in the demo video, I think I described the master output bus. And let's see here. All the ALU commands, their outputs will be pushed to the master output bus from the core output register. Which, let's see, I think this is ALU1 right here. Alright, so this is ALU1, and then we are performing an add command. Then as you can see, a 2 is coming out here, and we have a 2. And for some reason, we have a 1 here. Now this is exactly the reason why we are debugging, and it looks like it's coming from input. Alright, so actually this is expected, because, what is it? This computer has is hardwired in a special way so that the inputs here, if you read an input, it'll be able to cycle right back to the output. So that's why we have a 3 here in binary instead of a 2, which is the addition sum of 1 plus 1. As you can see here, the output is 2 from the ALU, but we are reading out a 3, and that's because the ones that we are dual reading here, and then this is the dual read bus. And if you guys want to see a how it works video and all the parts broken down, I will post that as well. Just ask for it in the comments, and then I'll do that for you guys, or I might do it in my free time. But this is the dual read bus. So this is read A, and then read B, cache A, cache B, as it's referenced in the doc. And the reason why a 3 is coming out instead of a 2 is because the inputs are hardwired to the outputs again, so that we're outputting the 1 that we just input in. And that's just made a little more useful for me and for hopefully for you programmers that are out there trying to program this computer. Alright, so we can safely determine that this is executing correctly because this 1 will go away when we go ahead and clock the next line of code. And we will do just that now. So, oh, and actually I completely forgot about the go to here. Since we tested for shift to overflow in the add command, as you can see, it's jumping to line 4 because we have not hit a shift to overflow yet. So as you see, line 4 is looking like the next command to load, next instruction. And then if we click increment line of code, again, it will go ahead and write output to RAM2 and output to decimal display. And if we look up here, if we're lucky, as you can see, we have a 2 up there, which means we did it right. And as you can see, it displayed a 2, not a 3. And that basically is confirming that, as you see, the 1 disappeared after that add command, or that add instruction. And we want to make sure that we're also writing this to RAM2, to RAM2, which we wanted to. And as you can see, we are writing 2 to RAM2, which is correct, which is good, which means our program is working the way it should. And now we are going to go to line 5, and then we'll click increment line of code. And I think this is a good time to bring up this next thing right here, which is right next to it. Command for wirelessly incrementing line of code. Let's do command. Now, basically, this command here, I'm going to copy this. This command basically makes it so that you can just paste it in and then hit enter, and then it will load the next line of code without you being here pressing this button all the time. And it can be extremely useful. And as you can see, we went through line 5, and then let's go back to line 3. And now the way to see if this flush command worked is that we can see, look up here in the master output bus. As you can see, there's no more data here because we've flushed the register, which is up there, which stores all the data. And now, if we go ahead and paste the command that I just copied, as you can see, the next line of code is loaded like that. And you see that's how it's useful, so we don't have to go back and forth from the debugger center. And now we are adding again, since remember we were executing the command before this one. And if we look in our output here, we should see a 4, or no, we should see a 3. As you can see, since 2 plus 1 is 3, since we are adding 2, which is in RAM address 2, and then 1, which is in RAM address 1. And as you can see, we're getting a 3 here. And then that is good, so it's working. And then we'll go ahead and load the next line of code, and that will do that. And now this will go ahead and output to the decimal display. If we give it a second, as you can see, 3. And then we should be writing this to RAM 2 as well. And it looks like our program is working. And now I'm going to go ahead and induce, that's kind of a big word here, but we'll go ahead and induce the shift overflow command here. So the way I'm going to do that is, I'll just leave this here, is that you can actually make changes to the data in RAM and in memory and stuff as the program is running, which is very useful for debugging. Since if I want to test that if that shift overflow command works, if I wasn't able to do that, I would have to wait for the program to cycle all the way from 1 to 255, which the program was designed to do since it counts. So I'm going to be a little sneaky here. What I'm going to do is that I'm going to go ahead and clock the next line of code. And as you can see, I can use that command anywhere, which is actually very useful indeed. So I'm going to go ahead, and as you can see, this is kind of advanced stuff. You don't need to worry about this, but I'm going to go ahead and write a 255 to memory. And you want to be very careful here since you might corrupt your memory, but I know what I'm doing since I built the computer. So, alright. So we have a 255 written in RAM address 2, and we went ahead and flushed that output register. And now we are jumping to line 3 again, so let's go ahead and add that. And now we should see that we're going to line 4, and then we should be jumping to line 18. As you can see, it just happened right there. Now, the reason this is because we have a 255 in RAM address in cache B, in cache A, and then a 1 in B, and we can't, there's no way to represent 256 using 8 bits if we go 0 to 255. We would require an extra bit on the right side, or an extra bit. And so, as you can see, our shift overflow has been triggered from here. And as you can see now, we are reading line 18, which is all the way down here, instead of line 4. And now we're going to be executing line 18 of code next. And as you can see, we only have 3 up there. But if I go and clock this, it will go ahead and, if we look, shut off the computer. And then everything should shut off. And then as you can see, the chunk updates are going a little high. Okay, so now everything should be reset. The program memory is reset. The RAM, if you want it to be reset, it'll reset as well. And I think it is reset. Oh, guess not. Okay, so I might have turned that off, but let's see here. Is that off? If it's not off, then we have a little bit of a problem here. Okay, so it is on. Alright, so I think, okay, so the debugger center is not hooked up to resetting the RAM. There is, however, a button over here that says clear RAM. And if you press that button, it'll go ahead and manually reset the RAM for you. So that's a little quirk of the debugger center, good or bad for you. And as you can see now, our thing here is completely reset, which is good. So the computer shutdown command is supposed to clear everything and then basically reset the computer, which it has done, which is good. And now we have tested our program. We have tested that it works. And a quick little thing to add, I will go ahead and go over the rest of this, the rest of the buttons here. This button here is teleport to user interface and control panel, which basically goes like up here. Then you can go back down here. And now these two buttons here, basically is what the computer does when you send a shutdown signal. So let's go ahead and load some lines of code into my computer here. So we have line 1 of code, then we have line 2. Yeah, we'll just load line 1 into memory. All right. So now if you want to go ahead and turn the computer off prematurely before you've programmed it to shut off, the way you do that is that you first press reset instruction registers, which will basically reset the what it's reading from. So now nothing's being read, as you can see here, and then nothing's coming out. So it's not reading any new instructions. And then you press computer shutdown, which resets all of the internal registers and all the memory and the RAM and the UI if you want it to. And yeah, our UI reset as well. So that's basically what these two buttons do. So if you want to turn off your computer, just press this button and then this one, and then you should be set. And so that is pretty much the Debugger Center in a nutshell. Alright, so we are back up here at the user interface here, and now that our program is tested to work, since we've tested it down here using the Debugger Center, we now can go ahead and actually execute our program, run it automatically. Now, the way to do this, the way to figure out what clock speed you want to run it at is that I would go ahead and start from the slowest clock speed, which is 111 here. And I think there could be another one, but it's alright. So 110, so 110. So the way this works is that whatever speed you want, you just input it in binary here. So then if we wanted 90 ticks, we would do 101, 100 ticks, 110, and then for 110 ticks, 111. Okay, so I did do it right. All right. So I have tested this already to work at 90 ticks, so 101, and I know that is ridiculously slow for modern Redstone computers in general, and especially just Redstone computers in general. But the reason for that being is because it's massive, and this is just a prototype after all. But a lot of you guys showed interest, which I'm very happy about. I didn't think I would get so much response from this. All right, so actually, the whole program is able to run at 90 ticks, but just the adding and stuff, so everything but the shift overflow can run at 50 ticks, since all of the conditions have a really big amount of latency, and that's pretty much one of the biggest caveats of this computer, is that most of the conditions are really slow to update, which I've been trying to solve recently. Wink, wink. So just to show you guys, since I don't think we're going to hit the shift overflow, which is like a while from now, we're going to go ahead and load line 1. I can turn this off. And now we're just going to go ahead and turn the computer on. And now that turns on, and then as you can see, oh, okay. So if you look on here, you can see that line 1 of code it's running, it's working properly. And as you can see, that's why the glass is here, so that you can watch the thing run. And if we let it run for a little bit, and then if you look up here, it'll show what line of code we're going to next. So now it's on line 3, we're going to line 4. Now it's on line 4 going to line 5, and then we should have a 1 coming up on here. And we have a 3 coming up on here. Okay. And okay, never mind, it's a 2. So that's kind of like the hardware in there doing its job. So this computer might do that occasionally. And if we just let the computer run a little bit, we will see the numbers update. As you can see, 3. So our program is working, as we just have tested and debugged, and there weren't really any problems with it, which is good. And then it should go to 4. We'll go to 4. It will go to 4. As you can see, it jumped to 7 a little bit because of that hardware in there, but it'll stay like that. And as you can see, our program is working successfully, which is what we wanted to do. So yeah, that is pretty much programming a super simple program using this computer.